comes to us from an Underwood Dudley number theory textbook, and I'm going to work part B. I think there's something that he didn't intend, maybe. We'll see what you think. But the author is Underwood Dudley, and his work is excellent. He's a great exposition and just a very good number theorist. I don't even know if he's still alive, but I really do enjoy the way he writes, and he's willing to, throw around his opinion without worrying too much about it. But I think, is it Dudley? I don't know if it's an EY or not. But anyway, I'm going to work problem B right here. It says, can you find an integer n such that 4 divides n, 9 divides n, and 4 squared or 16 divides n plus 2? Now this came from the chapter on the Chinese remainder theorem, and I think I know what he meant. But you can solve part B by very elementary means without using all of it. You see, I'm just going to use this piece and this piece right here and show you that that can't happen. So clearly an extra equation, it would still be impossible, right? So from this statement right here, that's the same thing as saying n is equal to 4k, where k is some integer. And also right here, this statement right here is equivalent to saying n plus 2 is equal to 16m for some integer m, okay? And this is very, very straightforward, no modular arithmetic required. If you subtract this left-hand equation, n equals 4k from n plus 2 plus equals 16m, the n's go away conveniently, all right? And you're just left with this statement right here. Again, this is subtracting this left equation from the right-hand side, and you can do that without having to write much down. It's fairly straightforward. So you get this when you do that, and notice we can factor a 4 out of the right-hand side. And so remember, m and k are integers, right? And so you can rewrite this. If you divide through by 4, you get 1/2 is equal to the difference of two integers, which of course is impossible. So again, by very routine means, no modular arithmetic, nothing sophisticated like the Chinese remainder theorem, if you want to call that sophisticated. But this is certainly impossible here. Okay, so let's write that down. Can be done. All right, we have proven, and I think what he wanted you to do probably is just go ahead and just chug right on through the, try to use the Chinese remainder theorem, and you wouldn't have relatively prime moduli. Right here, 4 and 16 aren't relatively prime, which is a condition required for the Chinese remainder theorem. Here, we have 3, 4, and 5. They're relatively prime, and all the requirements for the Chinese remainder theorem are met. Okay, but anyway, so the answer to the question is no. Okay, that's all.